All right. Good afternoon, everyone. My name is Troy Williams, and I'll be introducing our speaker today, Dr. Po-Yoon Chen. I want to thank everyone for coming in person and also those who are joining us online. And welcome to today's Lockheed Martin Seminar series on May 6, 2022. We have an exciting presentation by Dr. Po-Yoon Chen, who's an assistant professor in the Department of Chemical and Biomolecular Engineering at UMD. He's also affiliated with the Maryland Robotics Center. He obtained his bachelor's and PhD in chemical engineering from the National Taiwan University and MIT, respectively. After his PhD, he was awarded the Hibbett Early Career Fellowship and served as an independent researcher at Brown University for 2 years. After that, he worked as an assistant professor at the National University of Singapore for 2.5 years before now joining UMD. Dr. Chen has received many awards, some of which include the AME Young Investigator Award, the Shie 35 Under 35 Award. He was also named in the Inventors Under 35 in Asia by MIT Technology Review. He received the Shie 35 Under 35 Award and also was elected to the Global Young Academy, and he's also a fellow of Biblio. His research focuses on the intersections of nanomaterials and self-assembly, machine intelligence, and soft robotics machines. He seeks to create the synergy between machine intelligence and automated robots to construct high-accuracy prediction models, enabling automatic design of functional soft matter for soft robot machine applications. By implementing data augmentation and statistical analyses, he can reveal the underlying nanomaterial self-assembly mechanisms that dictate data-driven design principles. The insights gained from machine intelligence guided experiments can be utilized to fabricate sketchable electronics for wearable technologies and smart soft machines. Thank you, and Dr. Chen, take it away.
All right. All right. Can you guys hear me okay? Thank you for coming. I believe it's the last seminar for this MRC seminar. And I'm Po-Yoon. For people who don't know me, I joined the UMD last January, and we are starting a lab in the chemical and biomolecular engineering. So I'm a material scientist and also a chemical engineer. So I think I will just try to bring something material science innovation, and also how this material science innovation can combine with the machine intelligence to help us to design the soft robotic sensors. Okay, so today we are going to talk about our recent work. The title of today's talk is we are trying to utilize a data-driven design approach to design the soft robotic sensors. And then today we're going to show you we combine the machine learning and also the wet lab experiments, and to come up with a prediction model that can automatically design the sensor fabrication recipe for different parts of the soft robots. All right, let's get started. So this is the outline for today's talk. I'm going to talk about the introductions, like the background of the soft robot and the soft machines. And then I'll also mention a little bit regarding the needs and the challenge of the soft robotic sensor that can be utilized to measure the strength change on the soft robotic body. So today we'll focus on the strength sensors. My lab work on other kind of sensor, but today will be the strength sensors. So the first project I'm going to talk to you is this automatic strength sensor design, and we use this active learning. This is the machine intelligence algorithms, and also we do the data augmentation for us to create a model for the soft robot sensors. If we have time today, I'll go a quick overview regarding the rest of the project we are working on in my lab. But if we don't have time, we'll just end up with the automatic strain sensor design. All right. So let's see where we can get to. All right. So first of all, let's do the background of the soft robot and the soft machine introductions. So soft robot and soft machine, they, as you can see the figure over here, they are fabricated by using the soft matters. So unlike the traditional robot, they have this rigid body or the rigid links. They are using the elastomers. They are using the elastomers or the basically a silicone elastomer, or some of the people using hydrogel or polymer or paper, and to create these origami structures or these soft, like octopus-like soft robots. Okay, and then because the material they are using are intrinsically soft, and so they have outstanding compliance and adaptabilities. So when you control these soft robots, theoretically they have infinite degree of freedom deformations. Okay, so they give us a lot of the advantage compared with the conventional rigid robots. And because they are using these kind of the soft matter as their body, so the soft robot feature is lightweight and the fabrication cost will be lower. And also because the lightweight, you can use less power to drive this robot to actuate to do the task. So it's relatively power efficient. And those materials are easily to get access. Even a high school student in my lab can fabricate a soft robot and the soft machines. Okay, so one of the focus area in the soft robotic field right now is to give the soft robot the environmental perceptions or the self perceptions. And then the way normally people would do is to embed the sensors into or onto the soft robotic bodies. Okay, so as you can see, there are several examples over here. They are trying to embed the sensors to help the robot to understand themselves and to understand the environments and understand the objects they are dealing with. So, for example, for A over here, you can see that if we embedded the strain sensors into the soft robot, the strain sensor can provide these kinematic estimations indicating their deformation degree of the robot themselves to help us to achieve like feedback control. That you can, after you know how much they deform, you can control, for example, your pressure, your engine power to drive your robots to a certain location with high precisions. Okay, so that's a strain sensor. They can give you some of the kinetic perceptions. And pressure sensor can give us the information of their contact with the objects. So if, for example, you can see the bee, if they are grabbing something heavy or light, like a ball over there, if you have a pressure sensor, you will be able to tell the surface textures and then the weight and also the roughness and also the hardness of the object the soft robot dealing with. Okay, and the last category will be the chemical and biological sensors. They can also be embedded or put it onto soft robots to help the robot to understand the environments and to understand the situation, to help them to do the decisions for the next movements. Okay, so my lab focused on a lot on making those kind of the sensor for soft robots, ranging from the strain sensors to pressure sensor and those chemical and biological sensors. But there's a intrinsic difficulty is that most of the material developed for the sensors, they are designed for the rigid substrates. Okay, so because of the feature of soft robot, they have this infinite degree of freedom deformations. We require to bring those rigid materials from rigid surfaces to the flexible substrate or even to stretchable devices. All right, in order to integrate those sensors well with the soft robotic bodies. So today I'm going to show you how we're going to develop the stretchable sensor, especially the strain sensors, that move from the rigid devices to the stretchable devices, and then how we can utilize them as a wearable electronics or to make a smart soft robots. Okay. So, as I mentioned, we are going to focus on the soft strain sensor today. Basically, the soft strain sensors can give us the real-time kinematic estimations to help the user to achieve these closed-loop feedback control. Okay, and compared with the traditional way, like people will set up camera And to see the robots to move or to see the personnel to move within these coordinates, the soft strain sensor has the advantage is that you don't require those like heavy equipment. You don't have the restrictions of the certain coordinates. You can just wear those soft strain sensors and then move around, and then those sensor signal can be utilized to estimate the deformations or the movement of the soft robots. Okay, so compared with those earlier, the conventional approach, strain sensor has their own unique advantage. So that is people starting to put more of the strain sensors into the soft robotic bodies. Okay, so there are several of the challenge or the requirement for the soft strain sensor design, especially for soft robots. The first one is that your sensor need to be soft and compliant, indicating that you don't want to create like a rigid spot or rigid like a region on the soft robots to prevent your soft robot to move like extensively and then to stretch their body. You don't want to create that kind of limits, and you also want to be compliant enough that can attach to the soft robotic body and to allow them to actuate it with the soft robot. Okay, and then that can provide you the very precise of the sensor data of the strain sensors. The second challenge is to the second challenge is to provide a high strain sensitivity to your soft robot to the location that you put your sensors on. And then normally we will characterize the strain sensitivity by using this term called gauge factors, right? And then the equation of gauge factor can be seen over here. Let me see where I can annotate it. It's over here. So it's a relatively resistant change over the strain. So you want this gauge factor as high as possible, so that can reduce your noise ratio to allow your computer to recognize the movement precisely and in real times. Okay. The next challenge is that we want the strain sensor to be their working window to be tunable. Okay, so for example, if I'm a humanoid soft robots, I want to monitor the strain change of my shoulders. I also want to measure the strain change of my elbow, also my fingers. So the strain change of my fingers and my shoulder are different, right? So the strain sensor required for the fingers and the shoulder will be different. They'll need to have a different working windows. So the shoulder is probably about 30% of the strain range. The finger is about 80% of the strain range. So we need a high stretchability strain sensor for the fingers, but low stretchability of the strain sensor on the elbows. But both of them require to be with high strain sensitivity, indicating they need to have a high gauge factors. So you can imagine that the design logics for the sensors on the fingers and the design logic for the sensor on the shoulder will be very much different. Okay, so that is something we want our strain sensor design to be like a versatile and a tunable to fit the strain range of the location of the robot you want to monitor. The next thing is that there are several of the challenging sensing regions in the literatures. So the right figure over here, you can see we summarize some of the literatures, and then there are two kinds of the strain sensors. One is the capacitive type of sensors. Although they are very stable, but they have normally have a really low gauge factors. And another is because they're sensing mechanisms, intrinsics. So we are not focusing on the capacitive type sensors. We are focusing on the resistive type strain sensors. 1 second. Yeah. So, but you can see all of the literatures, they are only able to, their gauge factor continue to decrease when the stretchability increase. All right. So the challenge here is that it is really hard to get a really high stretchabilities and really high gauge factors. These kind of the features within one strain sensors. And also, if you zoom in here, when your strain is really low, less than 5%, there's no much work that can give you a high sensitivity within such small strains. Okay, so there are the two challenging sensing regions that for the decades, the entire literatures does not have like a very promising work for those two challenging sensor regions. And not to mention, there's no such a models that can predict the recipe for large regions and recipe for the high strength regions in the same times. Okay, so today that is the challenge we are going to deal with today. So if we look at the mechanism of the resistive type of strength sensor, it is based on one active layer, which is conductive. And then when you're trying to stretch this active layer from 0% to 60%, you can see that if you see the active layer under the microscope, you can see they are starting with this kind of crack formed on the active layers, right? So when you have more cracks, indicating your electron pathway get cut off more. So your resistance will go up along the strands. But this kind of the crack propagation behavior is very random. And then there's no good simulation model can really predict these random behaviors. So it is very difficult to use the traditional, for example, molecular dynamics or other kind of the simulations or FEA to mimic these random crack propagations. And this crack propagation is also very sensitive to the components that you use to synthesis or to fabricate these active layers. So as you can see that if we put some of the more carbon nanotube in there with one of the 2D material mixing, you can see by adding the CNT, you will push the stretchability as well. You'll push the stretchability. But if you add in the polymer into that, you will change the resistance curve like in the other directions. So in the literature, normally people will just fix the rest of the material and then change two materials because that is how humans good at it. Like in the optimize two parameters only. But as you can see, if we want to optimize multiple parameters together, that is out of like three-dimensional range for our brains. So we would like to utilize some of the machine intelligence to help us to optimize the recipe to fabricate these active layers for the strength sensors. So today we're going to show you our recent work using active learning and data augmentation to help us to prepare a model and to help us to design the fabrication recipe for the strength sensors. So some of the influential fabrication parameters that we found in the literatures, and then we do is listed over here. So as you can see, the strength sensor is a very simple device. It's look like that. So the brownish color substrate is an elastomer. It's highly stretchable. And then you will develop a strength sensing layer, which is normally conductive, and then they will generate a crack under the strain. Okay? And there are some of the fabrication parameters in there that you can play with. The first of all is the composition. You can change the composition of these strength sensing layers. So for example, we choose several of the representative nanomaterials, MaxIn nanosheets, single wall carbon nanotube, and polymer, polyvinyl alcohol, PVA. So these three materials are people normally use, and then combine it together, and then to make the strength sensors. Okay. Another degree of freedom we want to study is the thickness of these strength sensor layers. And another degree of freedom we can play with is the morphologies. So we can create different morphologies, like planar morphologies, or the periodical wrinkles, or the isotropic crumple morphologies onto these strength sensor layers. So if you do we have a white paper for me? Just a white paper is fine. I want to show you what does that mean of periodical wrinkles or the isotropic crumples. Just one white paper would be great. Yeah. So thank you. So the planar, normally the planar morphology is just like that. We fabricate a sensor, and then this is their strength sensing layer morphology. This is called planar textures. And periodical wrinkle is just we fold it in the microscale. Okay, and then we have these periodical wrinkles, and then we stretch the way perpendicular to the wrinkles. Okay, so that's the periodical wrinkles. And isotropic crumple is just we crumple these strength sensing layer and then put it back to the substrate. So you will have this random a crumple structure on the top of the strength sensing layers. And all of these three morphology have been shown in the literature that will have the effects on their performance of strength sensors. Okay, so let's take a look. Always use this one. Okay, so the first figures at the far right over there is that when you change the compositions, you will see that if you change the composition a little bit, like 8% of the vaccines for the red one to the black one, you will see the change, the resistance and the strain curve. This is normally how we characterize their performance. They will change, shift to the right. But when you continue to change, they will shift to the right and then with different shape, right? So it's really hard to predict of their linear compositions. Similarly, by changing the thickness, you'll change the stretchability as well. So these composition and the thickness, they are influential parameters. And morphology as well. By changing the morphology, you will be able to change your strength, stretchability of your sensors a lot. So we doing some of the preliminary data. We recognize composition, thickness, and morphology are three influential parameters that we can play with in the design space of strength sensors. So if we do a simple like a map, there are about 4 dimensions in this design space. So we have 3 components. If we fix 2 of them, we will be fixed the third one. So there are 2 degrees of freedom in the compositions, 1 degree of freedom in thickness, 1 degree of freedom in the morphology. So in total, we have 4 degrees of freedoms in our design space. So which is already out of my brain. I believe you guys probably can do it, but out of my brain of optimize it by designing experiments. So what we are trying to do, is to ask the help of machine learning to help us to optimize this 4 degrees of freedom design space. And then we're trying to make a prediction model that can do a 2-way design task. And these 2-way design tasks, one of them is that if I have my compositions, I have my thickness, I have my morphologies that I want to, in my recipes, I can directly, I don't need to do experiments. The model will predict the performance for me. And then the performance will be the same as the experiment I will do, right? So that will save your time, and I can watch Netflix just running this model without doing experiments, right? So this is the first, this way of design task. That will be really useful to save some of the experimental time. The next one is that we want to, for example, if I have a robot, so that is the fish robot that we're going to show you later. If I have a robot like these fish robots, and then I know the strain change of the fish robot fin is about 5%, and then I can feedback to the model, say, hey, I want the strain sensor that can sense the 5% strain change. Can you give me a recipe? The model should be able to find a feasible fabrication recipe for me. So the reason I emphasize feasible is that we want to create a model. They will not give you a crazy fabrication recipe. Say, hey, fabricate this sensor at 2,000 degrees C, or like a crazy competition. Like you will never be able to finish the fabrications. So we want to train a model. They can recommend a feasible fabrication recipe that you can do, or my student can do, to come up with the strain sensors for the specific soft machines. Okay, so this is our goal. So, but the thing is that machine learning is, as you know, is a versatile tool, but they are most of the time, machine learning are good for data-rich systems. So data is a problem. So how do we get enough data for the machine learning to do the accurate predictions? Okay, so a lot of the literature, they are using literature data. So I collect some of the data you have in your lab, I collect some data in your lab in the other school, and then I build up a model together for my strain sensors. There are three major problems that will come out if we use the literature data. The first of all, strain sensor, they don't have a standardized protocol to fabricate the strain sensors. You can come up with your own protocol. I can come up with my own protocol. Even 2 students of mine, they will come up with their own protocols. So the data quality will be low, right? So the way you fabricate will be slightly different. And if we collect from the literatures, the data quality will be low. And also, if we collect the data from the literatures, we'll always get unbalanced data. because most of the data you found in the literatures, their stretchability only report between 30% and 200%. But as I mentioned, the challenge regions is less than 5% and above 300%. Those are the soft robot region that we will deal with in the future, right? Like very large stretchability or very small vibrations. Those are the region we want to deal with. But the sensor, the data in the literature only focus on the 30%, 200%. So that will limit your view of your machine learning models. Okay, and most of the paper they will only report good data, right? So even my paper, if I don't do the machine learning, I don't report my failed data. So when I collect the data, I only have the good data. I don't have the bad data for me to do the correlations. So that is the problems getting the literature data, using literature data to build up prediction models. So how do we deal with these problems in my lab? So I really like these figures. Is that today's AI, machine learning, we are using a lot of the real data we collected by either external video, by using a video, or by using the sensors. But in the futures, these authors believe that the real data will be used as a base, and then they will create a synthetic data, and then utilize both of them together hybridly to train the model to optimize the accuracy of the machine learning models. So we are going to use the same way. We're going to do some experiments and then synthesis the virtual data based on the experiments and to fit into our machine learning model. That is something we're going to show you. That we are using both synthetic data and the real experiment data to train the models without using any literature data. Okay, so I can generalize the steps of building up the models I just mentioned by doing 3 steps. The first step is to do boundary definitions, all right? And then we're using very classic, just SVM classifier to plug away some of the regions that in the 4-dimensional design space. So the gray region over here is the regions that experimental-wise we are not able to finish, right? So we need to block those away for the model. So the model will not recommend the recipe over there, because even the model recommend the recipe over there, students or me or my postdoc cannot do the experiment to finish to get out that kind of strength sensor. So we need to block those away. And the next thing we're going to do is active learning. So active learning, we just do it stage-wise to collect the representative data in the 4-dimensional design space. And this approach will help us to minimize the amount of the experiment we need to do, and then to navigate the entire 4-degree design space. The last one I'm going to do, as I just mentioned, I will going to synthesize the virtual data based on the experiment data we collect, and then to optimize the accuracies of these prediction models. Okay, so those are the 3 steps. And then let's do it step by step. The first step is to do boundary definition. We're trying to block some of the portions of the design space away for us to only focus on the feasible recipe or feasible competitions. So when we're doing the experiment for the strength sensor, what we are trying to do is to filter. What we're trying to do first is to filter the materials. We filter polymer, 2D material, and CNT onto membranes. Okay, and then we'll peel off the membranes from the filtration membranes, and then we'll take these active layer film onto a stretchable substrate. But during this process, when we try to peel off, some of them are easy to peel off. Some of them, when you peel off, they crack. Some of them, they will just want to stay on the membrane, and you will not be able to peel off. So we categorize them as a feasible, fragile, and fail. And then we do 351 mixtures across the composition design planes. And then, this one. And then we found out that, so this is the left-hand side, the right-hand side here, the block one is the failed competitions. Those competition, if you use the competition of, for example, this is 80 of the PDA and 10 of the CNT, and the other 10 will be your 2D materials, these data will fail. You will encounter the failed experiment over there, like they'll just stick onto substrates. So we do a 351, and then find out that this is my region. The green region is the region that I will focus on. Those are the region I can peel off the membrane, peel off the active layer from the membranes. And then we do SVN and you turn these discrete data into a heat map. And then the feasibility becomes the possibility of detachments. Okay, and then we set the bar around like 0.8 possibility of detach the film as our threshold, and then we'll only focus on the green regions in the compositions, in those compositions over there. Okay, so that's the first stage to define the boundary of our design space. For the second step, it's called active learning. So we are starting to do the experiments. By first of all, we do some random experiments. By just random experiment with random of the fabrication recipe. So we fabricate 10 in the very beginning, and with a random recipe, and then we measure their sensing performance. And then we take out several points of the sensing performance profile, and then combine them as one data point for each recipe. And then we will combine it together. So we have 10 recipes, we have 10 data points in here. And then we fit into the decision tree and then ANN models. And then they will come out with 6 decision programs. And these 6 decision programs will starting to calculate the unfamiliar, they will calculate the entire design space. They're trying to find out the data points that they are not unfamiliar with. So they are far away from, the green dots is the one we have, they are the experiment we done. And then the red one are the one with the highest variance, from the 6 decision program, and then they are far away from the already known data points. Okay, and then they will locate land and then feedback to us, and then we will we'll let them pass the SVN to see whether they are in the green in the green region that we are able to do experiments, and then we do the experiment again, and then to turn those red dots into the green dots. And then the green dots will, and then when after those red dots become the green dots, we'll do another predictions to explore the entire design space. Okay, so we're just doing and then this is one active learning loop. So by doing so, we are able to stage-wise to understand the entire design space with minimum amount of the experiment we need to do. So as you can see, we only do 125 of the strength sensors, and then 46 of them are G0. G0 is the planar, with the planar morphology code is G0. G1, 1D, we have 31, is the wrinkle one, with the periodic wrinkle. G1, 2D is just how we call the crumple textures. Over here, we have 48. So 125, you can see the model kind of like equally suggests us to do the experiment to understand the design space for each morphologies. Okay, and then we do 12 rounds basically and 12 rounds takes about 2 months to finish the design space navigations. And then we have 2 ways to monitor to determine when we should stop the active learning loop. So as you can see, we see the MSE first. This is the arrow of the design space. The arrow of the prediction model. In the very beginning, the blue dots over here, the arrow is really high, indicating they are not able to predict the test data really well. All right, and then but suddenly when they kind of navigate enough of the design space, they are starting to fill in the internal dots between the boundary and the inner boundary and outer boundary. The MSE drop quickly at around round 6, round 7, and round 8, and then getting stabilized to around round 12 over there. So we just feel like, okay, we're running out of time. We just stop around round 12 and then utilize that for our base before the data augmentations. Okay, so that is the one way is to see the MSE, and L bar is another way to see it. That L bar is to estimate the degree of the space explorations. So in the very beginning, you can see that when we have a very few data, that they are trying to predict the point that are really far away from them, And then after that, they were starting to fill in. These L bars starting to decrease, indicating they are explored in the 1 to 4 activating loop. They are trying to see the point outside, and then when they touch the boundary, they're trying to come back to investigate the points between the outer boundary and the inner boundaries. All right, so you can see that the L bar decrease before the MSE decrease. So that is one of the evidence that the model is trying to put in more dots in between the boundaries and boundaries. Okay, so the next thing is that, as I mentioned, those are the real data. 125 are my real data, and I want to save my students' time and save the sensors. Making sensor require money, so I want to reduce the cost of building up this model. So we utilize two data augmentation methods. One is called SMOP, REG. One is called user input principle. And then I'll just briefly talk about the difference between these two methods. The SMOP REG is the green dots is the dots you know, and then we do the linear regulations to generate the dots in between the two real data points over here. So that's the code SMOP. And UIP is we just proliferate the data, the virtual data around the real dots around it. Okay, so this UIP is very similar to is very useful because when we're doing these simple preparations, we found out that by changing 2% of the compositions, the sensor data looks the same. I mean, and then that 2% is very small of the variation in our compositions. So we can generate a data points by pushing the composition 2% away, but I'm still using the same data points, same sensor data points, and that can help us to generate the virtual data points. So after that, we will be able to increase our data points from 125 to about 10K. Okay, and then these 10K of data will also decrease the overfitting problems in the machine learning model. Okay, and after that, we will utilize this called genetic algorithm selection to select the decision programs that can give us the best predictions performance, and then that will be our champion models for our strength sensor design. Okay, so that's too technical. And then you can see this one is that by using all of the approach we just mentioned, we are able to push the relative error from 49 to 30 to 26 to 24. All right, so we can continue to do that by just using this in silico approach by generating the synthesis data. Okay, and then we are using independent testing data to evaluate their prediction accuracies. Okay, so this is the result of the predictions. So the green dots over here are the real experimental data in the test data. So the model does not know anything about the test data. So if I'm using the one with our data augmentation, you can see this is the blue one with our data augmentations. They are predicted far away from the experimental data. But after you starting to put a data augmentation in there, you can see they can predict the red dots over here. It is starting to become really close to the experimental data, so which we are satisfied to utilize them as the champion models. Okay, so and the next one, we are finally have the model. We can utilize them to design the strength sensor for the soft robots. So the case one I'm going to show you is that we utilize this model to design the sensor for the soft gripper. So the first thing is that we're trying to measure the strain, the strain of your soft grippers over soft grippers on the outer edge of their fingers. And then we found out that when they're trying to grab a bottle, it's 90% of the strain. When you're trying to grab the other kind of bottle, it's 28% of the strain. So we can fit in those design requests is that I want a gauge factor, which is the sensitivity, larger than hundreds, and then their stretchability is between 19% and 28%. Okay, and then normally when we're trying to design this, when you're trying to satisfy this design request, my student need to do a lot of experiments to try and error to see what kind of the morphologies and what kind of the composition is the best for these soft robotic grippers. But right now, we just put in these requests into the model. They will come out a recipe for us, and we fabricate it based on the recipe, and then they do fit us. They do show the very sharp change. The sensor number 1 is one kind of recipe. Sensor number 2 is the other kind of recipe, and then sensor number 1 does give us pretty good sensitivities within these 18%, 19%, and 28% of the strength. So we can utilize that to attach to a soft gripper to help us to identify their pneumatic actuations. Another example is these. We use these. We are collaborating with underwater soft robotic lab. They have these soft gripper. Sorry, not soft gripper. These soft robotic fish, and then they want us to design the sensors for their fin. And then their fin, as you can see, their strength change is only about 1%. And 1%, as I mentioned earlier, 1% is within the challenge regions of the strength sensor design. Conventional, commercial one strength sensor is normally about 10% of the strength change. They are fine with it. 10%, less than 5%, you're starting to get a lot of noise. Your signal to noise ratio will be low. So, but we also fit in those requests into the model. They come out with 2 recipes, and then within 1% of, and the red highlight bar is the 1%. And then we choose the sensor 2 because you can see that the sensor 2, the slope of the sketch factor is huge here. So we choose the sensor 2 and then and utilize our recipe and then put it back to the fish. As you can see from the figure on the right, we put up 5 sensors on the fin. 1, 2, 3, 4, 5 sensors on the fin, and then utilize them to monitor their flapping behavior in the waters. So we have some videos to show you. So this is the soft swimmers robots, and you can see the left fin over there. There are 5 sensors attached to the fin, and because our sensors is soft and compliant enough, they are still allow the swimming robot to do these like navigation routes and without disturbing their swimming patterns. And we also can real-time monitor their fin like flapping behaviors. So we have like a 5 sensor integrated in there. So we can, and we tested when they flap. You can see when they flap, they were starting to have these peaks show up. And if you count the number of the peak, that will exactly the same times of the flapping numbers of when they categorize from the videos. And we tried 3 different frequencies of the flapping behaviors. The strength sensor are able to detect and to tell the same frequencies that we set in the soft swimming robots. Okay, we also trying to connect our sensors with wireless chips. So, and then we utilize them to wirelessly to monitor some of the soft exoskeletons for rehabilitation analysis. Okay, so we just when we put our sensor into these soft exoskeletons, we are able to tell how much of the strain that apply to these soft exoskeletons. Similarly, we also try like hand exoskeletons. We can also connect to the wireless chips, so we are able to. This is the received wirelessly, so we are able to tell what kind of objects we are grabbing because the strain of your soft exoskeleton hands will have a different strain change, basically like that. Yeah. Okay. So that is more application part. So the other thing we can do is that we collect 125 sensors, right? And then one of the drawback people always feel like the machine learning is that it's a black box. No one knows why machine learning do that decisions. So a lot of people trying to drive the machine learning to explainable machine learning. So what we are trying to do that as well. But what we are trying to do it by doing a static analysis to understand the decision-making logics of machine learning models. Okay, so the first thing we do is that we list out all of the 125 sensors out and look at their working windows. So we found out that the models is interestingly can predict a some of the very crazy stretchability to 350%. Some of them will be really small to about 0.3% only. So if we use the literature data to train these models, the model will be really hard to give those kind of data because we only fit in the data within 30 to 200%. Okay, but if we're using our own data, we are able to, the model will be able to push us to the limits of the design space to give out those sensors with within the challenge regions. So 0.3% and the 350% are both well located in the challenge regions in the literatures. Okay, and then we'll continue to do the data analysis to see whether there are some usable design principles. So the first one we do is to do the Spearman rank correlation analysis to see to find out whether there's a strong monotonic correlations between the recipes and the performance. So we found out that there's, based on the three figures over here, we found out an interesting correlation in G0, G1-1D, and G1-2D sensors. In the G0 sensors, you can see that we have CNT ratio, PBA ratio, and the thickness, those degree of freedoms. Which one we should change to move the performance of the sensor a lot? We found out that thickness is the one which, if you want to change the G0 performance, changing the thickness will be most effective approach. Changing CNT and changing PBA, changing the composition, will not have strong effects. Similarly, we are able to use a data analysis to tell G1-1D, if you want to change the performance of G1-1D sensors, changing CNT and changing thickness have equally influential effects. G1-2D, instead of changing thickness, changing the composition will be more influential, will be the most influential. So we also do another kind of the data analysis called SHAP. So this is again theoretic approach to explain the output of machine learning models. So I'm not going into detail, but from SHAP models, the data analysis results are also very similar, saying that for the G0, thickness is dominant effects to control the sensor performance. And G1-1D will have like equal influential parameters in the G1-1D sensors. Okay, and so because of these two data analysis give us those conclusions, we take those as a data-driven design principles. All right, to finish this talk, because I think we are about the right time. So I'm just trying to summarize some things. Is that we develop a method which is hybrid by using wet lab experiments and also machine intelligence to construct a high accuracy prediction models. So they can do a two-way design test by predicting the performance based on the recipe, or come up with a recipe based on the performance you want. Okay, and then we developed a three-stage machine learning framework, including SVM classifier, active learning loop, and data augmentations. And we are able to do this inverse design task for the strain sensors for different kind of the soft machine or the soft robot that can be utilized in the water or wear on the body. Yeah. Okay. So this is the work we recently published in the Nature Machine Intelligence, and then they also write a highlight review for this work. Yeah. So I think that is kind of like today's talk. I don't think we have time to go through the last stage, but let me show you some of the nice videos. So my lab is trying to bring the 2D materials into the soft matters, and then to create some new soft robotic materials that have the intrinsic advantage compared with the silicon elastomers or the hydrogels. So let me show you some of the quick videos over here. So first of all, we trying to put some of the clay, nano clay, into the elastomer, onto the elastomer, and then make these crumple structure on the surface. So it's like giving them a fire-retardant skin for the soft robots. And then these fire-retardant skin, they will have those wrinkle-like structure. When you stretch, the fire-retardant skin will not break apart. They will just actuate it with the elastomers. So we can make the soft robots become fire retardants, so they can grab the objects from the fires. We also can put it onto the glove. So you can see those are nitrile glove in the lab. If you, what's that? One sec. Yeah, maybe I can play it like this. If you put a nitrile glove to the flame, they'll burn immediately. But if you have those fire retardant coatings onto the glove, even you make your glove larger, they can in contact with the ethanol flame, and then without like generating the flame. Okay, so that is safe for the people that are dealing with the ethanol burners, basically. Okay. And then by using the similar method, we are able to make some of the stretchable batteries that can utilize onto the robots. These are the stretchable batteries, and we also can make. You can see this is the battery we are making, and then we can stretch these batteries, and then still have a really good capacities and good recharging capacities. We also can make a stretchable heaters that can be wired on the closings, and they also can do like heat management for the closings. We also have these. We also make it as a stretchable EMI shielding layers. We guys using foam a lot. There's an EMI wave around it. Although there's no report saying that this EMI wave is harmful, but people still have concerns. So we are trying to make this EMI shielding, which is stretchable, that can be embedded into the fabrics to prevent those antennas wave that gets into your body. But so we also using a similar way to make these wearables materials that can be utilized as protection robots. We also work with the hospital to make the stretchable pressure sensor for the transoral surgical procedures. So you can see those of the image over here. These are the transoral surgical robots. They are hard. Those are hard robots with multi joints. So when they go into your transoral regions, they will scratch your transoral regions with a small scratch and then injuries over there. So we designed the pressure sensor for them that is very delicate. When they touch a little bit of your tissues, they will respond like strongly signal back. So the surgeon will know they need to move away from that region to avoid like a unnecessary scratch. So that is the pressure sensor we will also play with. I think that will be kind of everything I want to present it to you. So thank you for the invitation, and thank you for your time attending this seminar. And thank you for your introduction as well. Yeah.
All right. Thank you, Dr. Chen. We're going to open up the floor to some questions. Does anyone have any questions? Okay, I guess I have a question.
Sure.
So there was a part in your slide where you discussed developing recipes.
Yes.
Right, for the strain sensor? Yeah. Okay. And what specifically drives those recipes? So for example, can you say that you want a particular goal for a particular sensor? Mm-hmm. Maybe that you don't care about strain above some threshold, right? You only are going to operate within a certain fixed range or something else. Can you specify those goals to?
Yeah. So for example, we use a finger as example. For finger is about the biggest strain is about 80, okay. And then normally it's 0, so it's a 0 to 80 range. So that is the working window we want to. You want your sensor to be able to detect those working window. Is that the question you want to ask? I'm not 100% sure. Yeah.
To some extent. So basically, you want to specify some goals that you want your end sensor to have, right? Or to meet. Yeah. I should say.
So that is the working window. So the model we design is basically want to meet the working window of the robots. So if your robot has a specific working window, for example, the gripper robot has 20 to 30, normally you need to try different kind of commercial sensor to see which one is the best. But the model can just decide it for you, which recipe will come out with the sensor that can fit the 20 to 30% of the windows over there. But they are not, I mean, the model is not strong enough to give you the entire a performance over there, but they can direct you probably a champion recipes within the design space. Yeah. Cool. Thanks.
Any other questions?
All right. Thank you for coming.
All right.
Yeah.
Well, thank you so much for everyone for coming and those who are online. And we'd like to thank Lockheed Martin for sponsoring these series. And thank you again, Dr. Chen, for presenting.
Yeah. Thank you for inviting me. Yeah. Have a good weekend, guys.
All right.
Good weekend.